1:23:40. Senior Reactor Control Engineer Leonid Toptonov places his hand on a button marked AZ5. Emergency Protection Number 5. A system created to save a nuclear reactor in a moment of crisis. He presses it. 43 seconds later, 190 metric tons of uranium fuel, the radioactive heart of Reactor 4, will be hurled into the atmosphere above Soviet Ukraine. But here is what almost no one knows. Pressing that button did not stop the explosion. It caused it. The safety system, designed to prevent a core meltdown, became the trigger for the worst nuclear disaster in human history. This is the story of how an atomic reactor was destroyed by its own emergency brake, and why the people who tried to save it never had a single chance. April 25th, 1986, 5 p.m. The city of Pripyat lay spread out 2 kilometers from the Chernobyl nuclear power plant. Population 49,000. Average age 26. The youngest city in the Soviet Union. A wedding banquet is underway at the White Stork restaurant. Children ride bicycles through courtyards between concrete apartment blocks. From every window, the power plant is visible. 4 giant stacks release white steam into the spring sky. A source of pride, a guarantee of prosperity, the atom tamed and put at the service of man. Inside the plant, shift supervisor Alexander Akimov receives an instruction from Kiev. Reactor 4 is to undergo a safety system test during its scheduled nighttime shutdown. This test had been postponed for years, delayed, reviewed, delayed again. But tonight, it will finally be carried out. The goal is to prove that in the event of a total blackout, the reactor's own turbines can still provide residual power for a short time. Enough to keep the cooling pumps running until the backup diesel generators come online. The gap to be bridged was only 40 seconds. On paper, the solution looked elegant. The test was personally overseen by Deputy Chief Engineer Anatoly Dyatlov, 50 years old, steel gray eyes, a reputation for being brilliant and ruthless at the same time. He had worked in the Soviet nuclear submarine program. He did not tolerate objections, hesitation, or weakness. His subordinates feared him more than the reactor itself. Unit 4 was an RBMK 1000 reactor. Graphite moderated, water-cooled, a design unique to the USSR. An enormous machine, 7 meters tall, 12 meters in diameter, with 1,661 separate fuel channels running through a mass of graphite blocks. Maximum electric output, 1,000 megawatts. Thermal output, 3,200. The reactor had been operating for only 2 years, the newest and most modern in the complex. But the RBMK had a secret, a defect built into the design itself. At low power, the reactor became unstable, prone to sudden power surges. The water cooling the fuel also absorbed neutrons, and thus helped restrain the reaction. If that water turned into steam, if voids formed in the cooling channels, fewer neutrons were absorbed. More neutrons meant more fissions. More fissions meant more heat. More heat meant more steam. Feedback. A train with no brakes. Engineers called it a positive void coefficient of reactivity. In practice, it meant one thing: the reactor could accelerate its own destruction. Soviet designers knew about this feature. They also knew that the control rods, the main safety system, took a full 18 to 20 seconds to enter the core completely. For a reactor going into runaway, that was an eternity. But the RBMK was cheap to build and produced weapons-grade plutonium as a byproduct. Economics and military interests outweighed safety concerns. In 1986, 15 RBMK reactors were operating in the USSR, all with the same hidden defect. By midnight, preparations for the test were in full swing. Reactor power had to be reduced from 3,200 megawatts thermal to a range between 700 and 1,000. A smooth, controlled reduction. But at 11 p.m., something went wrong. One of the operators failed to switch the control system from automatic to manual at the right moment. Power did not decrease gradually, it collapsed, from 3,200 megawatts to 30 in a matter of minutes. The reactor nearly died. At that power level, the reactor began poisoning itself. Xenon-135, a fission product that actively absorbs neutrons, filled the core. The reaction almost went out. The fuel was smothered by its own waste, deprived of the neutrons needed to sustain the chain reaction. Dyatlov entered the control room at 12:30 a.m. His face turned to stone when he saw the power level. 30 megawatts. Unacceptable. The test required at least 700. He turned to Akimov and Toptonov, raise the power immediately. Akimov hesitated. The instructions were unambiguous. Below 700 megawatts, the reactor enters a dangerous operating regime. Continuing the test violated several safety requirements at once. He said so carefully and respectfully. Dyatlov's voice turned quiet and icy. "I did not ask for your opinion. Raise the power." It was at that moment that Soviet obedience culture became a weapon. The hierarchy was absolute. The word of a superior was law. Contradicting a senior officer could mean the end of your career, reassignment to some remote facility in Siberia, a mark that would follow you for the rest of your life. Akimov and Toptonov exchanged glances. Then they began withdrawing the control rods from the core. The control rods in an RBMK reactor are made of boron carbide, a material that absorbs neutrons and slows the reaction. Under normal conditions, at least 30 rods were supposed to remain fully inserted to preserve a safe control margin. The instructions required a minimum of 26. But as Akimov and Toptonov pulled out rod after rod, trying to revive the poisoned reactor, that number kept falling. 20, 15, 10. By 1 in the morning, they had managed to stabilize the reactor at 200 megawatts. Not 700 as required, but for Dyatlov, that was enough. He ordered the test to continue. At that moment, only 6 to 8 rods remained fully inserted in the core. The reactor was hanging literally on the edge. Almost all the brakes had already been removed. But that was not the only problem. Under the test protocol, several safety systems had to be disabled. The emergency core cooling system, off. Some automatic emergency shutdown signals, blocked. These decisions were not considered reckless. The test was meant to simulate a total loss of power, which meant systems that would not function under those conditions had to be disabled here as well. On paper, it all looked logical. In practice, it meant that if anything went wrong, the automatic protection would no longer intervene. Toptonov was 26 years old. He had worked at the Chernobyl plant for less than a year. He sat at his console, staring at the instruments, his hands trembling. Beside him, Akimov, 33, experienced, respected, kept glancing at Dyatlov. Both men understood they were operating outside safe parameters. But neither stopped the test. On the wall of the control room hung a poster. Every nuclear power worker must remember, nuclear reactors are safe, but only in the hands of attentive and responsible people. Leonid Toptonov would die on May 14, 1986, of acute radiation sickness. Alexander Akimov on May 11th. Anatoly Dyatlov would survive, serve 3 years in prison, and until his death in 1995 would insist that the disaster was caused by the reactor's design, not by his decisions. He was partly right, but only partly. Both the design and his actions were to blame. At 1:23, the turbine test began. Steam was diverted from the reactor to see whether the turbines, spinning by inertia, could still generate residual electrical power. But diverting the steam meant reducing the flow of cooling water through the core. Less cooling meant higher temperature. Higher temperature meant more water turning into steam. Inside the reactor, invisible to the operators, the chain reaction was already accelerating. Steam voids were forming in the fuel channels. Neutron absorption was falling. The rate of fission was rising. More heat, more steam. The positive void coefficient was tightening its grip on the reactor's throat. The operators saw that power was rising again. 200 megawatts, 300, 500, then faster still. The instruments could no longer keep up with reality. Former workers described the characteristic sound of that night. A heavy, rhythmic, muffled pounding from the reactor hull, like an enormous heart. Those were the technological channels vibrating as steam voids formed and collapsed, while shock waves passed through thousands of tons of metal and graphite. At 1:23:40, the power rise became exponential. 800 megawatts, 1,000, 1,500. Akimov saw the readings and understood what was happening. The reactor was entering an uncontrollable runaway. He shouted to Toptonov, "AZ5! Press AZ5!" Toptonov slammed the button. All the reactor's control rods, all 211 of them, began descending into the core at a speed of 40 centimeters per second. Boron carbide rods meant to absorb neutrons and choke off the reaction. This was supposed to work. It was supposed to stop everything. But that was exactly what guaranteed the explosion. Here is what Toptonov did not know, what the other operators did not know, what the Soviet nuclear authorities concealed even from the men operating the reactors. The RBMK control rods had graphite tips, 5 meters of boron carbide meant to absorb neutrons. But the first meter to enter the core before anything else was graphite. And graphite is a moderator. It does not absorb neutrons. It slows them to the speed most favorable for fission. In other words, it accelerates the reaction. The graphite tips were an engineering compromise. They reduced wear in the channels, displaced water more effectively, solved a dozen smaller technical problems. But at the same time, they created a deadly paradox. When such rods are inserted into a reactor already entering runaway, graphite enters the core first, not boron. And for the first 3 to 7 seconds, the reaction is not suppressed, it is intensified. This defect was known. In 1975, a partial accident occurred at the Leningrad nuclear power plant. An RBMK reactor experienced a power surge under a similar low power condition. The influence of the graphite tips was recognized as one of the factors. The Soviet nuclear industry studied the problem, documented it, and classified it. Plant operators were not informed. The design was not corrected. When Toptonov pressed AZ5, he thought he was stopping a runaway reactor. In reality, he was driving an accelerator into it. Imagine pressing the brake pedal, and for the first 3 seconds, instead of braking, it steps on the gas. You are certain you are stopping. But in fact, you are guaranteeing the accident yourself. Inside the core, the reaction rate doubled. Then doubled again. Power, 3,000 megawatts, 5,000, 10,000. The instruments hit their limit. Fuel elements began to fail. The zirconium cladding ruptured. The uranium dioxide pellets, ceramic cylinders in which the energy of burning tons of coal was concentrated, shattered. The cooling water flashed into steam in microseconds. Pressure rose with nowhere to go. The temperature in the core shot above 2,800 degrees Celsius. Metal melted, concrete cracked. The reactor vessel itself, built to withstand colossal pressures, began to come apart. Steel seams ruptured, bolts were sheared off. Fuel channels, each of them a pressurized tube containing uranium and zirconium cladding, tore open simultaneously at hundreds of points. 33,000 megawatts, 10 times the reactor's design maximum. Energy comparable to a small nuclear device, but released not in a fraction of a second, but over 43 seconds. Slow enough for the reactor to tear itself apart from within. 1 hour, 24 minutes, 23 seconds. 43 seconds after AZ5. The reactor exploded. Not once, twice. The first was a steam explosion. The superheated coolant instantly vaporized, creating monstrous pressure. The 2,000-ton reactor lid, a massive steel and concrete disc the operators called Elena, was thrown upward like a coin. It rose, flipped over, and crashed back down at an angle, partially opening the core to the air. 2 seconds later came the second explosion. Its nature is still debated, possibly hydrogen. At extreme temperature, water split into hydrogen and oxygen, and the mixture then ignited. Possibly a brief, uncontrolled burst of nuclear reaction. Not a nuclear explosion in the sense of a bomb, but a release of fission energy so violent that it tore the reactor apart for good. The roof of the reactor building was ripped open. A column of fire and debris shot 300 meters into the night sky. Graphite blocks, weighing several kilograms, were scattered across the plant grounds. Pieces of uranium fuel either vaporized or were thrown outside as fragments. The graphite, superheated and exposed to oxygen, caught fire. 50 tons of nuclear graphite began burning like a blast furnace. Radioactive smoke entered the atmosphere. In the control room, the lights went out. A few seconds later, emergency power came on. Red alarm lamps lit up across every panel. The dosimeter sirens howled continuously, a high, cutting sound. Akimov and Toptonov stared at the instruments in shock, their hands still on the controls. The dosimeters read 3.6 roentgens per hour. Not good, but not catastrophic. The problem was that the number meant nothing. Those dosimeters simply could not display anything above 3.6 roentgens. That was their ceiling. The actual radiation level in the control room was later estimated at between 1,000 and 5,000 roentgens per hour in certain spots. A dangerous dose, 500 roentgens total, could be accumulated in 6 minutes. Dyatlov burst through the door. His face was pale. Akimov looked at him and said, "The reactor is destroyed." Dyatlov stared at him. Then his face hardened again. "Impossible. The reactor is intact. You are mistaken. Check the instruments." He simply refused to believe it, could not accept it. The reactor was considered a structure capable of withstanding monstrous loads and any conceivable accident. An RBMK could not explode. It was not just a technical installation. It was a dogma of the Soviet atomic project. Dyatlov ordered Akimov and Toptonov to continue emergency cooling, to pump water into the reactor to cool the core. They obeyed. For hours, they remained at their posts, directing water into a reactor that no longer existed, receiving a greater and greater lethal dose with every passing minute. Outside, workers on the night shift heard the explosion and ran toward Unit 4. Sasha Yuvchenko, a mechanical engineer, was near the reactor hall when everything blew. He saw a huge concrete block, part of the upper biological shield, flying through the air like a leaf caught by the wind. He saw a pillar of light shooting upward from the destroyed reactor hull, bright white with a bluish edge. Ionized. Air, the sky itself glowing with radiation. He ran to the edge of the destroyed hull and looked down. "I saw something I would never forget," he would say later. "There was no roof. Above me were stars, and below the fuel was glowing, not red, white, like looking at the sun." Yuvchenko received an enormous radiation dose that night, and yet, by some miracle, he survived. One of the very few who looked directly into the open core and lived. At 1:28, the call reached the Pripyat fire station. Lieutenant Vladimir Pravik and his crew arrived within minutes. They saw fires on the roof of the turbine hall and near the reactor building. Around them lay burning pieces of black porous material, strangely light, like coal. The firefighters picked them up with their bare hands and threw them off the roof. Each piece was a block of reactor graphite, emitting monstrous radiation. A few seconds of contact was enough for a dangerous dose. Pravik and his men worked through the night. Within minutes, they felt a metallic taste in their mouths, tingling on exposed skin, nausea, headache. This was acute radiation injury in real time. Cells breaking apart, bone marrow shutting down, radiation tearing molecular bonds in their DNA. Vladimir Pravik would die on May 9th, 1986. He was 23 years old. His body would be so radioactive that he would be buried in a lead coffin sealed in concrete. By 5 in the morning, the fires on the roof had been extinguished, but the core itself continued to burn. 50 tons of nuclear graphite, exposed to open air, burned at a temperature of around 1,500 degrees Celsius. And that fire would continue for another 9 days. When the sun rose over Pripyat on the morning of April 26th, plant director Viktor Bryukhanov made his first report to Moscow. Minor accident, reactor intact, radiation under control. Why did he lie? Because the Soviet bureaucratic system punished those who brought bad news. To admit that the reactor had exploded meant destroying your career and possibly going on trial. Bryukhanov hoped the situation could still be contained, brought under control, somehow hushed up. Later that same morning, civil defense units arrived with proper dosimeters, military instruments capable of measuring extreme radiation levels. Near the destroyed reactor, they recorded 30,000 roentgens per hour. That was a level at which survival was impossible even briefly. A lethal dose could be received in a minute. By noon, the Soviet leadership already knew the truth. But Pripyat, a city 2 kilometers downwind, still had not been evacuated. Across Europe, radiation sensors were already beginning to trigger. A cloud of cesium-137, iodine-131, strontium-90, and dozens of other isotopes was spreading across the continent. Sweden detected it first, then Finland, Poland, Germany. The world was already beginning to ask questions. In Pripyat, April 26th was a beautiful spring day, sunny, warm. Children played outside. The wedding in the city center continued as planned. Some residents complained of headaches, nausea, and a metallic taste in the mouth. They thought it was the flu. Meanwhile, invisible particles, microscopic fragments of nuclear fuel, dust carrying isotopes that would remain dangerous for centuries, were falling from the sky like snow. At 2 p.m. on April 27th, 36 hours after the explosion, buses finally arrived in the city. The 49,000 residents of Pripyat were told to take only the essentials, light belongings, as if they were leaving for just 3 days. A temporary precaution. They never returned. The city was emptied. Dinners remained laid out on tables. Toys were left in children's cribs. The amusement park in the city center, which was supposed to open on May 1st for the holiday, remained silent. Its yellow Ferris wheel never carried a single passenger. Pripyat became a time capsule, a city frozen at the moment of evacuation and slowly decaying under the burden of radiation. But the disaster itself was far from over. The core remained open. Wind carried radioactivity across Ukraine, Belarus, Russia, and farther into Europe. If the burning graphite could not be smothered, if the molten fuel burned through the concrete base and reached the groundwater, the contamination could enter. The Pripyat River, the Pripyat flows into the Dnipro, and the Dnipro supplies drinking water to 30 million people. Kyiv, Kherson, the Black Sea. The Soviet state mobilized. Helicopter crews were ordered to drop sand, clay, lead, boron, and dolomite onto the burning reactor, smother the fire, seal the core, bury it. The pilots flew directly over the open reactor, hovering in clouds of radiation and manually dropping sacks of material. On every sortie, their dosimeters hit the limit. Pilot Nikolai Melnik made 30 sorties in the first week. 30 times he hovered above an open nuclear reactor, breathing air saturated with radioactive particles, while the instruments in the cockpit malfunctioned from electromagnetic interference. He survived. Many of his comrades did not. On the ground, the Soviet army created what they called biorobots. At first, real robots were sent onto the roof of the reactor block. Remote-controlled machines meant to clear debris. They failed. Radiation burned out their electronics within minutes. And then people did what the machines could not. Soldiers were sent onto the roof in shifts. Each was given 90 seconds. 90 seconds to run out onto the roof, shovel fragments of graphite and fuel, push them off the edge, and come back. Some received a lifetime safe dose in less than a minute. They wore lead aprons that did almost nothing. Dosimeters screamed continuously. One soldier left, the next replaced him. Over the following months, more than 600,000 people took part in the liquidation effort. Soldiers, firefighters, miners, engineers, conscripts. Conservative estimates speak of 4,000 deaths linked to radiation exposure. Other estimates are much higher. Thousands more developed cancer, immune disorders, and genetic damage passed on to their children. By November 1986, a giant structure had risen over Reactor 4, object shelter, known as the sarcophagus, 30 stories high. 430,000 cubic meters of concrete and steel. It was built by people working in extreme radiation fields in shifts of just a few minutes, pouring concrete and welding metal while their bodies slowly broke down. It was never intended as a permanent solution, only as a temporary shelter, a bandage on a wound that could no longer heal. The sarcophagus stood for 30 years. By 2016, it itself had begun to deteriorate, leak, and threaten another collapse. A new enclosure, the new safe confinement, was built beside it and slid into place on rails over the old shelter. A steel arch weighing 36,000 tons, designed for a service life of 100 years. But the radiation inside will remain dangerous for 20,000 years, longer than all of recorded human history. The consequences of Chernobyl spread across 150,000 square kilometers of territory in Ukraine, Belarus, and Russia. 350,000 people were permanently resettled. In Belarus, childhood thyroid cancer rose 90-fold because of exposure to iodine, 131. The design defects of the RBMK were finally addressed. The control rods were modified, safety systems strengthened, but only after the catastrophe. Soviet secrecy and the slow response humiliated the Soviet authorities on the international stage. Some historians believe Chernobyl accelerated the collapse of the Soviet Union because it exposed the rot inside the system too clearly. Dyatlov, Bryukhanov, and chief engineer Nikolai Fomin were found guilty of criminal negligence and convicted. Dyatlov served 3 years. Then he wrote a book, gave interviews, and until his death, he insisted that the real cause was the reactor's design. The positive void coefficient, the graphite tips on the control rods, and he was right, but he was also the one who ordered the test to continue, ignored warnings, and drove the reactor into an unstable regime. Both statements are true at the same time. The blame lies not only with the design and not only with one man, with both. The control room of Reactor 4 seems frozen at 1:23:40. The AZ-5 button still preserves the imprint of Leonid Toptonov's hand. 43 seconds later, everything exploded. 43 seconds in which more radioactive contamination was released into the atmosphere than in the bombings of Hiroshima and Nagasaki combined. 43 seconds that turned an entire region into a forbidden zone. 43 seconds that proved that the atom, no matter how domesticated it may seem, is never truly under our control. The Chernobyl exclusion zone still exists today. 30 kilometers in every direction. Nature has returned there. Wolves, bears, wild horses roam through abandoned villages. But the soil is poisoned. There is cesium in the bark of the trees. If those forests burn, radiation will rise into the air again. And in a very real sense, Chernobyl is still burning, still dangerous, still a monument to what happens when human ambition, institutional blindness, and engineering defects converge at a single point. 43 seconds. Nothing more was needed.